Welcome back to part two of our introduction to the naming and drawing of organic molecules, the nomenclature and representation. Okay, so in part one we saw straight chain alkanes. Here in part two we're looking at cycloalkanes, alkanes which make cycles. And the first cycloalkane is a 3-carbon ring. And so, yeah, this ring, this cycle, is clearly the inspiration for the name cycloalkanes. And so this is called cyclopropane. Okay, this is the first one because it's pretty hard to make a ring out of 2 carbon atoms, so there's no cycloethane. And certainly you can't do it with one, so there's no cyclomethane either. Right, the molecular formula for cyclopropane, you can see that each carbon has 2 hydrogen atoms. So it's C3, 3 times 2 is 6. Okay, now compare that molecular formula C3H6 with the molecular formula for propane. All right, here is a reminder of the structural formula for propane. And so therefore it has molecular formula C3, count the hydrogens, there's 8. Okay, why does propane have C3H8 versus cyclopropane having C3H6? Well, look at these carbons on the end of the chain of propane. They each have 3 hydrogens, but in cyclopropane, each carbon only has 2 hydrogens. So propane has 2 hydrogens more than cyclopropane. And this pattern will repeat for every cycloalkane that you care to look at. Okay, cyclobutane will have 2 hydrogens less than butane. Cyclodecane will have 2 hydrogens less than decane. Okay, one can draw a structural form for this. Okay. There's a condensed structural form. Okay, now I've done something here which you may not have seen before, which is instead of writing CH2 there, I've written H2C. And the idea behind this is to emphasize the fact that the thing that's providing connection to multiple atoms in the rest of the molecule is the carbon. That carbon down there is the highlighted carbon is connected to 2 other carbons. So it's the carbon which is making these connections, okay, not the hydrogens. If I'd written that highlighted section as CH2 and had the lines pointing to the hydrogens, one might form the impression that the hydrogens are somehow making more than one bond. They're providing connection, and they are not. So you will often see this in the drawing of organic molecules. Okay, so we have the molecular formula C3H6. We have the structural form at the top there. Underneath we have the condensed form, and here is the skeletal form, my favorite. Voila, done. Okay, each vertex of that triangle represents a carbon atom, and implicitly each carbon has as many hydrogens as is necessary to ensure each carbon has 4 bonds. Okay, each one of those carbons is making 2 bonds with other carbons. Therefore, each carbon needs to make 2 more bonds with hydrogens in order to ensure they will have 4 bonds. Okay, there's cyclopropane. Next, 4 carbons, cyclobutane. Butane has molecular formula C4H10, but this cyclobutane is going to have molecular formula C4H8. 2 less hydrogens because we don't have hydrogens on the ends with 3 hydrogen bonds each. Okay, I'm going to skip the structural form. I'm just going to draw the condensed structural form. And here is my favorite, the skeletal. Boom. Okay. Now I'm not going to step through every cycloalkane up to cyclodecane. Let me just talk about one more, which is a very frequently occurring kind of structure, one where you have six atoms making up the ring. So this is cyclohexane. Each carbon has two hydrogens, therefore the molecular formula is C6H12. Okay. Here is a possible condensed structural representation. Okay, it's a bit skew-if. And here is a, let's try and make this a little more elegant. There we go. There is a skeletal representation of cyclohexane. Okay, so cyclohexane, the ball and stick representation really comes into its own here, because the information that it conveys, more than the structural form could convey, is the fact that those six carbon atoms, you can see they're not all sitting in the same plane. They have this sort of slightly wonky bent structure, and that's because if you want to force those carbon atoms to all sit in a plane, you have to bend the bond angles in a different way than what's shown on the screen here, and that requires more energy. So this conformation on the screen right now is a low energy, and it's a stable configuration. Yep. If you somehow were able to coerce this molecule to have the six carbon atoms all sitting in a plane, that'd be higher energy and be unstable. The moment you stop doing whatever you were doing to make it sit in that plane, it would sort of snap back to this and release some energy. Okay, that is our intro to the naming of cycloalkanes. See you in part 3.